In the last year, Capital One invested heavily in something called Technology College, where all the different courses and information is stored for any Capital One associate to take a course. And also, there is an opportunity for all Capital One associates to submit the course, and that's how we share knowledge. It's a huge database of the materials that are available. So I would like to present to you Zach Hanif. He's a director of machine learning at the Tech College. And he leads the enterprise-wide Center of Machine Learning with Capital One. Please welcome Zach.
Hi. Thank you, everyone. So I know that we've all been here so fairly early, and getting closer and closer to lunch, so hopefully this goes relatively well. I was just introduced, I'm a director of machine learning inside of Capital One, although my legal department compels me to state that nothing inside of my presentation is an official position of Capital One in any way. I'm personally really glad that Spark has supplanted the original MapReduce framework. It has specifically made my life as a machine learning practitioner much easier, specifically in allowing us to have stronger pipelines for data processing and starting to produce more and more scalable algorithms that we can run over infrastructure that not just modifies our data and transforms our data, but also puts our data into an area that we can learn from it. In particular, I'm very interested in applications of Spark to accelerate machine learning pipelines and tasking. In a much larger sense, I'm interested in automated and repeatable experimentation. One of the biggest things that most data scientists that I know have to work with and have to deal with on a regular basis is the fact that experimenting inside of machine learning can be very tedious. Recording your results, making sure that you've modified each and every little parameter. There's a lot of fiddly knobs and dials you have to deal with. And it's something that I'm particularly passionate about, finding ways to make this more accessible for humans so that we don't have to spend our entire lives trying to record every single thing we do in an Excel-based lab notebook. It's my basic thesis that unless we make tasks like that more automated, we as a community will never be able to bring our technology into the forefront where it needs to be. We will never be able to approach all the different areas that machine learning can benefit us. The agenda today is relatively basic. We're going to cover an introduction to automated model optimization and specifically the no free lunch theorem. We're going to cover 4 basic topics. What is a hyperparameter and why do we care about optimizing it? We're going to figure out what the implications of free lunches are in regards to the NFL theorem. We're going to discuss some optimization strategies in practice. And we're going to discuss some of the caveats and drawbacks of using automated hyperparameter optimization, because it is not a silver bullet. If you've been doing this kind of thing in operation for a while, this talk is probably too introductory for you. We're going to be covering grid search and random search and a couple of the basics of theory, but I'm not going to stand up here and go deep into the current state of the art of Bayesian optimization, nor am I going to discuss particle swarm optimization, which is another area that's getting a lot of academic interest recently. So let's get started. Hyperparameter optimization is what all of this really is about. Parameters are a specific term inside of machine learning. Parameters of your function are what you instantiate, the hyperparameters are what you instantiate your function with. They are the things that the function doesn't natively adjust, and they instead determine how your function's weights, the parameters, are in fact adjusted. They form the boundary conditions of your algorithm, and they can have a dramatic effect on your algorithm's efficacy. They govern how and what your model learns. The majority of machine learning frameworks that ship with out-of-the-box implementations of common machine learning algorithms will generally have sane but non-optimized defaults. And the reason for this is somewhat obvious. They can't know what parameters you need to set for the data that you're going to run on. In the same way that all of the weights, the parameters themselves that you're training, are modified based on the training data that is presented to the algorithm, the hyperparameters are also to be tuned in accordance to the data that you give it. Now, they're a little bit coarser. They're not quite as fine-grained for manipulation. But the number of trees, for example, inside of a random forest is ultimately a function of the kind of data that you're presenting to it. It's this kind of modeling that leads to some fairly significant accuracy and efficacy improvements over time. Machine learning models, as we kind of all know, are mathematical functions that represent the relationship between different parts of data. And training that model is really the act that you build out this model of the world, the model that you are going to use in the hope that it's generalizable to data that you haven't seen before. I've referenced decision trees as kind of a clear and obvious example that everyone should be fairly familiar with. And the main hyperparameter that everyone has to deal with at some point inside of a random forest or inside of a decision tree are the number of trees that you have, or what your the Guinea metric you want to use is. Support vector machines require a misclassification penalty term, and kernelized SVMs require setting kernel parameters, like, for example, the width for a radial basis function if you're using an RBF kernel. So optimization for hyperparameters is the problem of optimizing a loss function over a graph structured configuration space. And in somewhat easier terms, that effectively means that hyperparameter optimization is how you tune what the algorithm is going to do, so that way you're able to ensure that you can learn more quickly, more efficiently, or more accurately. Hyperparameter optimization in literature these days tends to be discussed in the context of neural networks. And in fact, the papers that I'm going to be citing today throughout the course of this presentation are written by some of the premier neural networking researchers. But at the end of the day, hyperparameter optimization is something that is done across pretty much all forms of machine learning models. Working inside of neural networks, if anyone in here does that, you definitely know how many various little knobs you have to twist and turn and manipulate. This gets more and more apparent as you start to move down the path of deep learning, where you have dozens, if not hundreds, of layers. But we're not going to go down that path. We're going to discuss this in somewhat more accessible terms today, focusing on algorithms that have been implemented in MLlib. Traditionally, hyperparameter optimization has been done by humans, literally by hand, fiddling with these individual values, recording their experiments inside of a notebook of some kind. And this was done because computerized trials, only just even several years ago, were extremely expensive. And hardware advances and cloud offerings have substantially moved kind of the lever there as far as economic efficiency in allowing algorithms to search over a very broad space. So why is this helpful? Anyone who's ever trained a random forest has seen how the adjustment of the number of trees that comprise that forest will affect the overall accuracy of the model. Now, accuracy is a term I'm going to use a lot in here, and it's a bit of a loaded term at the end of the day, and we'll discuss that in a little bit, but for now, I'm using it effectively as shorthand as a measure of our model's efficacy, right? Our goal in pretty much any case is to have the most effective model possible that can be robust when presented with previously unseen data. And that's the general goal of machine learning in general. I'm going to show you a practical example now, an instance of a Zeppelin notebook that I stood up with a MLlib model loaded into it. Give me just 1 second here. Good, that works perfectly. So let's take a look at this. What I've got right here is just a simple example of an MLlib model. The data that backs this is Kaggle's Titanic data set. So there's some interesting things that you can go out and read about if you want to see how that goes. And what's important in this talk is not the fact that we've trained the best possible model to determine whether or not someone survived the sinking of the Titanic, but is instead more of is more relevant for this discussion, because we're going to see how just small changes to hyperparameters can have large effects on the overall efficacy of the model as a whole. So anyone who's not already familiar with kind of the MLlib syntax and how things work, this is our setup of our random forest classifier. And if you take a look down here, these 4 fields that we're setting are our hyperparameters. We're setting the number of trees that we have. We're setting our impurity measure to the Guinea. We're setting our max depth of each tree to 2. And we're setting that we're only going to have 10 bins total. There's a little bit of extra material here that kind of gives us an example of what we're doing. We're using pipelines that are built into MLlib after MLlib 2, and a few other things that kind of make this a little bit easier, but I'm going to execute this now. And as I quietly sit here and pray that my demo does not betray me, we're going to see that our area under the rock curve, which is what we're using as our measure of efficacy, comes out to 0.77. That's really not too terrible for something that we haven't spent any time optimizing in any way. But let's take a look at what happens if I don't change anything else. I'm not changing our feature engineering. I'm not altering how we work our pipeline. I'm not altering our data in any way. Let's see what happens if I simply just change the number of trees that we have from 5 to 50, and we change our max depth from, say, 2 to 8, 2 arbitrary numbers that I just pulled out of the hat. Our model trains again, and we've gone from 0.77 to 0.879, right? That's a meaningful improvement. And that's something that that's effectively what we're going to start exploring here today, right? I just picked those 2 numbers that I changed here. I just altered those 2 hyperparameters randomly. I picked 2 individual numbers simply because a tree depth of 2 is a little bit silly at the end of the day. But if I'm actually trying to find what the optimal selection of hyperparameters are for this model, as it trains over this particular data set, I can either sit here and adjust a large number of things with a very large combinatorial space, or I can allow my machine to make those changes for me. And the purpose of this first demo, just to recap, was to demonstrate that relatively small changes to effectively how the model is going to learn can have a meaningful effect on the efficacy of that model without having to go back and spend a lot of time changing your feature engineering or bringing in additional data. Let's go back to the slides. So a quick word on all of this. If I'm up here claiming that we can programmatically optimize the parameters for a model, haven't we solved machine learning? If we can just do this programmatically, right, why are machine learning engineers and data scientists really employed at the end of the day? Isn't what they do just more or less setting things up and letting an engine kind of churn over the overall search space? The answer is no, we haven't. And for anyone in here who is a hiring manager and saw that and was saying, oh, good, we've got this, we've solved it now, I'm very sorry to disappoint you. The majority of models that we're encountering in real life, particularly in the area of supervised learning, are going to have implementations that have sane, if non-optimal defaults for our specific problem sets. And it's that phrase there, non-optimal defaults, that's particularly important to us. I don't know of too many applications of machine learning in the real world where we don't care about gaining another couple percentage points of accuracy with relatively little effort, right? And there's a certain point where you start getting diminishing returns and you're fighting for 1/100th of a percentile point, and maybe or maybe not that's a big deal. But at the end of the day, if you're using machine learning, odds are pretty good that you're running through large amounts of data, and a percentage point or two can have an enormous effect kind of on how much you have to get back and actually validate your results and how you perform in the real world. The other thing that I'll state is that feature engineering as a whole is still wildly more influential. And frankly, improving your data in the first place is even more so. And this is most famously discussed in the 2009 paper, The Unreasonable Effectiveness of Data, and the somewhat more recent 2017, I think it's only 2 months old now, revisitation of that concept that's been published by Google. And then finally, data scientists still need to sort out whether or not they're working with a model that might be completely inappropriate for the problem at hand, right? So that way we can at least come up to the statement of, well, we need to search the hyperparameter space, but we don't necessarily need to search both the hyperparameter space for algorithms and then search all the possible algorithms that we could apply to a problem. There's still a lot of things that humans are involved in. But the big important takeaway is that we've now made something that was previously the pure domain of humans tractable by machines. So I referenced the no free lunch theorem a little earlier on. And the no free lunch theorem is effectively the mathematical property that makes this work very relevant. Why is this an area of academic research that we care about? So the formal definition of no free lunch was published in 1997 and in a follow-on paper a year after that entitled The No Free Lunch Theorems for Optimization. And this is the most general case. Theorem 1 says that given a finite set V and a finite set S of real numbers, you're able to apply that and transform it into a search space where you can choose uniform experiments from that set according to a uniform distribution for all possible functions from V to S. And that actually goes even further and says that for the problem of optimizing a function f over the overall set V, there's no algorithm that performs better than blind search. And that's the formal definition, which, if you're anything like me and tends to read formal definitions instead of hears them dictated to you off of a podium, that may not have been terribly enlightening. So let's break that down a little bit. The no free lunch theorem, or NFL as it tends to get referred to a lot, is actually a combination of two theorems. One for supervised machine learning that was published in 1996, and then one for search and optimization, which is a more general case, that was published a year later in 1997. The no free lunch theorem asserts that if you have a supervised or even unsupervised statistical model with an objective measure of efficacy, as for example the rate of misclassification, then there are no a priori distinctions between learning algorithms. Effectively, what this means is that you don't know what your best model is necessarily before you start experimenting. And that's at the model level. In terms of the actual hyperparameters for an individual model, that problem is only more apparent. And it implies that there are algorithms that perform better than others based on the nature of the data set, which then are necessarily worse for all other data sets. So if you're better in one area, you pay for it by being worse in others. And we don't know what those areas are before we start our experimentation. And so this implies that the best way to select both an algorithm and a set of hyperparameters is to try all of them, to experiment across the entirety of the space. We don't know which algorithm is going to perform best when we're starting with a new data set because we don't understand the true underlying statistical distribution of that data set. If we did, there wouldn't be much of a point in doing machine learning in general. We would have just simply solved this because we're, somehow psychic. The logical result, therefore, is that we're incentivized to not just search the potential space of hyperparameters for a single algorithm, but to search the space of all applicable models as well. Some of you who have been introduced to this concept before should be looking at this right now and saying that this is hideously expensive in terms of computation. We'll address that in a minute. One thing else that I'm going to mention kind of early on inside of this is that all of these optimization strategies are intrinsically tied to evaluations of efficacy and your overall set of evaluation strategies. For the purposes of this talk, because evaluation strategies for machine learning algorithms is its own subfield of research, quite frankly, for the purposes of this talk, we're going to focus on k-fold cross-validation, where if you're not introduced, you split your data into k number of bins, you withhold a single bin for testing, and you use the remaining bins as training data. You iterate through this process k number of times until you've iterated withholding every single one of the bins. This is one of the main reasons for using cross-validation, and specifically why inside of Spark and MLlib, the cross-validation estimator is the primary way that people actually do grid search inside of Spark, simply because it's such a robust means of doing evaluation. Is it always the best? Probably not. But is it a relatively good means for going through and getting to a reasonable state? It absolutely is. In general, this is a fair way to properly estimate model prediction performance when you have unbalanced data, which is probably always going to be the case for most real-world applications. Let's take a look at another set of Zeppelin demos. So I've talked about grid search, and I've talked about actually performing this, right? I've demonstrated up here with the first example that if we change a couple of our hyperparameters, we start to see changes in our evaluation, how effective we are based on the loss function that we're trying to optimize against. But if we go down here and we start looking at grid search, that's where this starts getting a little bit more fun and probably a little bit more applicable for people who are using MLlib and Spark in general. Up here, I'm defining my parameter grid, right? The range of values that I want to iterate over as I begin training my algorithm. So I'm going to say here that I want to modify the maximum number of bins. I'm giving it 3 values that we can iterate over. The maximum depth that we're going to use, a depth of 1, 2, and 4 for our respective trees, and how we're going to measure the impurity of each individual tree in the random forest, either using a basic entropy measure or going back to the Gini measure. I'm going to emit right here how many tests this actually represents. Those of you who can do short multiplication in your head know that this is going to be 18 individual trials that we have to iterate through. And then everything else is more or less identical to the previous trial that I did above. Literally all of this is just boilerplate that got copied directly. At the end, I'm once again going to print our efficacy. And simply because I'm very cautious, I have executed the cell beforehand, but I'm going to re-execute it now and quietly sit here and sweat as this runs for about a minute and a half as it goes through all of the individual trials. Everyone in here who's done presentations, especially if you have a live demo, knows that the most stressful part of the presentation isn't looking out at the number of people staring at you. It is actually running something in a live environment. And foolishly, I keep getting up on stages like this one and actually executing stuff in live environments, kind of trying to taunt the demo gods to smack me down sooner or later. So hopefully today won't be the day. In the event that it is, however, I've at least run this beforehand and I can talk to a previously saved result. Spark is great for this kind of work. One, because parameter optimization is embarrassingly parallel, which Spark is natively great at. But the other thing that works really, really well for us, and particularly when we're using Spark, is that it expands the amount of data that we can pass to our algorithms. MLlib's implementations are quite solid, and they definitely do a very good job of making sure that we don't have to pressure one individual node constantly to be able to train over large data sets or relatively complex trees. So fortunately, my material finished, and let's scroll down here. I'm hoping that this is visible. I'm not sure the contrast is the best on the screen behind me, but let's take a look at this. This is what our parameter map actually looks like, and this is an array that represents all of the individual trials that we're going to run. So we're running a trial here using our entropy and purity measure. We're going to use 10 bins as our max, and we're going to have a max depth of 1, and it goes so on and so forth from there, trying all of them. And if we scroll down here, we'll see that compared to our original run of this, where we simply picked values at random, our best measure here, our best model in the overall set of the pipeline, comes out to having an efficacy of 0.827, right? So doing better than our original guess for parameter values, which gave us 0.779, if my memory serves. Let's go back. Before we kind of move on to some of the practical measures of this, I should probably mention that in the more general paper that was published, the 1997 paper for the NFL theorem, it also applies towards non-supervised problems, generic search problems. Really, anytime you've got something that you've got an objective loss function to search over, the NFL theorem definitely applies. In general, however, there are two caveats. One, it only applies to data sets that are comprised of finite spaces. And two, it assumes that algorithms are not continually resampling points across a finite space. But any and all algorithm that fits those two metrics, which is most of the stuff that we're going to be dealing with in a practical sense, will be able to be applied. The no free lunch theorem applies to those algorithms. So for any and all algorithms that are optimizing a cost function, they will perform exactly the same when averaged over all possible functions. And just one more time, just for why this is so important for us, for any optimization algorithm, any superior performance for an algorithm over one type of problem or data set means that performance over others will suffer. Model selection on the whole can definitely be a tricky thing, and I don't necessarily advocate for trying every single model and every single hyperparameter for each of those models in a brute force fashion. General knowledge and guidelines about underlying data and algorithms are still definitely needed to avoid a lot of unnecessary exploration. Trying everything that your library offers on every data set that you're presented is probably a way to become A, wildly inefficient, and B, charge up a very, very large AWS bill. Additionally, trying models may not always be as simple from an engineering perspective as parameter optimization is. For the most part, parameter optimization is a little easier from an engineering perspective. You've got a set of values, you simply instantiate a series of trials, and you measure the efficacy of each one of those. Whereas depending on the machine learning framework that you're working with, there are certain frameworks that may or may not make certain assumptions about the kind of data that you provided. You may need to do additional data feature engineering to be able to work with all the various algorithms that may be presented to you. MLlib is actually pretty good about this. They've got a fairly normalized set of API calls for running each individual model and for training them, which makes this actually a little bit easier for MLlib in practice. Last time about the no free lunch theorem in practice before we start talking about how we actually optimize our functions directly. We can't have a priori knowledge about which models are going to be ideal for a given data set, and past experience only gets us so far. And that's simply because we don't understand, as humans, the underlying statistical distribution of the data sets that are presented to us. If we can't know which model is best, how then could we know what hyperparameters are best for each individual model, if not through actually experimenting with it? And this prompts two questions. How are we going to search such a large space efficiently? And two, computational resources aside, why isn't this the only way we actually train our models? And it's a good thing we're asking these questions now. So optimization in practice. No matter what we're dealing with, optimization is a search problem, and search is broad and extremely expensive if you're attempting to be exhaustive. You incur meaningful costs for every single retraining event. For the examples that we simply had above, the simple random forest algorithm that I ran in the beginning more or less finished executing by the time I was able to address the fact that it finished executing. In the case of the grid search that I ran, it took about 1.5 minutes. And sometimes that cost can be meaningful, as you see here. Depending on your optimization strategy, there's a lot of state that needs to get communicated during training events, effectively the meta experiment that you're running, so that you can guide where you go into your next training. You see that inside of particle swarm optimization and the Bayesian optimization algorithms, which we're not touching on today, but you'll see that meaningful state that has to get communicated. And then finally, if not properly constrained by humans, the search space can be gigantic. Previously, we had to run 18 experiments to finish our, one of the demo runs that I had there, and that was only having a handful of things that were, again, picked more or less at random that represented our range. Spark comes in and benefits us here simply because it is able to run large experiments very, very quickly, but still at the end of the day, these are costs that we are going to need to represent. So Spark, like I said, is highly distributed, and since optimization search is embarrassingly parallel, this is very, very good for us. Spark right now runs in a manner so that we're not running multiple experiments at the same time. This is probably less efficient than we want it to be, since we're effectively pipelining our overall set of experiments so that we wait for experiments 3, 4, and 5 until experiment 1 has completed and 2 has completed and so on. There are a handful of tools that are out there, which we'll discuss kind of towards the end of this presentation, that actually run this in a truly parallel environment. But it's not really that bad. Just because Spark isn't taking full advantage of the embarrassingly parallel nature of this problem, it's giving us a couple of other things. One, it's behaving the way we natively expect it to. So we're looking at this and saying, okay, well, if it took 15 nodes to be able to train a particular model with the amount of data that's being presented to it, and now I want to try an optimization step, which has to run 4 or 5 experiments, you're still using all 15 nodes to train each experiment, as opposed to divvying up that overall space of nodes. This is a UX concern at the end of the day, but it definitely leads to a lot less confusion. And then the ease of access to data that we get inside of Spark really can't be overstated. The fact that we've got execution and data occurring usually co-resident on the same node, or at the very least over a bulk network link, is something that dramatically speeds up the work that we're doing in a distributed environment. Finally, model complexity tends to increase with the size of data and the bounds of which the decision space is guarded by, and this makes a distributed solution extremely useful. Spark's got a handful of strategies that make this a little bit easier to work with, just from a engineering angle. The pipeline functionality definitely improved this, because I had to implement random and grid search in a previous company when we were on Spark 1.6. It wasn't a lot of fun. The pipeline functionality definitely makes this a lot easier, and the fact that Spark now implements grid search natively has radically improved the quality of life for machine learning engineers all over. Optimization strategies. I referenced grid search and random search a handful of times. And grid search is particularly important inside of Spark because it's the only one Spark natively implements. There's a couple of GitHub projects running around right now that implement random search, and there's only one that I know of that implements a Bayesian-based search inside of Spark. And when you take a look at them, you're going to see one of the downfalls of the Spark architecture, which is that pipelining system. The pipelining system makes a lot of things significantly easier, but it does also cause people to have to implement a great deal more code when they're implementing these search strategies themselves. As a general rule of thumb, this is actually kind of a problem for Spark. Grid search is generally falling out of use in favor of random search strategies, which are significantly more efficient, and now Bayesian optimization, which is receiving a lot more attention from the academic community. That's okay, though. Just because Spark doesn't have the most efficient thing currently implemented inside of it, its general benefits are large enough that it's still worthwhile for us to do this work. It definitely results in a meaningful lift for developers, as we've kind of already seen. It's just something that you have to consider and be aware of when you're starting to run these tasks. So grid search, which I've referenced a few times now, is arguably the most commonly implemented parameter optimization solution. I'll admit that I haven't taken an exhaustive survey of what's been implemented in open source. Grid search effectively runs off of a set of models where you have a number of different parameters that differ from the other ones, and they all are laid in a grid. That wasn't the best explanation that I could have given, but there's an image at the very end of this that should make things a little bit easier. What you do is you lay out all of your various parameters in a space across a grid in an attempt to make sure that you're hitting one of the points that you lay out will hit the global optimum for the combination of parameters that you have available to you. You try them all, and then eventually you select your best one. Our intuition is that if we lay our optimization space out on a grid and try every single possible combination, we will eventually find the presumed global optima. This is a method of doing effectively exhaustive search. It's a bit painful. Random search is one of the things that in about 2012 started to eclipse grid search, certainly in the area of not machine learning, but deep learning. Random search instead explores a subset of provided parameter values and therefore allows the user to explicitly control the number of parameters tried and therefore the number of experiments that get run. This can often result in a substantially smaller number of trials necessary to reach a near optimum, if not optimum solutions. It does, however, appear at first glance that this would lead to worse results than an exhaustive grid search, but it usually is better for people simply because of the fact that you're getting very close to an optimal state in far, far less time. There's a paper that was published in 2012 that goes into this in great detail. So let's look a little bit more deeply. Let's imagine a space of parameters where 5% of all of the possible points in that space represent observations around the true optimum. For each random experiment, therefore, we've got a 5% chance of being one of those observations. So we've got a simple probability problem at the end of the day. We want to find the optimum given a certain probability of discovery. Let's say we want to have 95% certainty that we found the optimal point in that overall space. And so we solve for a relatively simple equation there. And the reference paper down below comes up with a statement that says for a number, for 95 percentile accuracy, for 95 percentile certainty that we've reached a near optimum space, you only need about 60 trials. And that should be enough to explore that space. As opposed to grid search, which is a more or less exhaustive search over the entirety of the space, this is worlds better for an improvement. And of course, you can modify the percentile of assuredness whenever you need to. So this is the image that I was referencing a little bit earlier. The grid layout is on the left side for the audience. And on the right side, you've got the random search space. You'll note that at the very top, that green curve up at the top there represents where we believe the optimal space to be, the optimal set of parameters. In a grid layout, we miss it. We miss it dramatically, actually. And the only way to get around that is to increase the number of points on that grid, which can lead to very substantial increases in our overall training time. Whereas when working with a random layout, we are probabilistically more likely to hit a couple of points on that overall peak of a curve. And we can evaluate each of those trials and knock out the ones that weren't as effective. This image is actually taken wholesale from the 2012 paper that I've referenced earlier because it's a really great way of kind of explaining this. And they've got a very nice formal definition, which is pretty accessible for anyone who's just trying to read it relatively quickly. The failure of grid search, they claim, is the rule. They claim it's far more likely when sampling the exact same number of points between the two strategies for a grid search to fail you, therefore necessitating far more sampling inside of the overall search space, as opposed to a random layout, which is almost guaranteed to find a near optimal space for the same number of points. So I've referenced a few caveats before now. There are no There is no silver bullet. There is no panacea. Machine learning problems are very, very hard in general, not just simply due to the mathematics, but because of the way they represent business intent. And these methods are just options in a suite of tools for developing accurate, robust models. Ultimately, these techniques make eking a little more performance out of your models possible, but they don't remove the need for humans in machine learning, not at all. And all of these techniques pale in comparison to the efficacy generated by improving your data or your feature engineering techniques, which, with the exception of some deep learning problems, are still squarely inside of the domain of human beings. These approaches have three major drawbacks. One, they increase the risk of overfitting. Two, they meaningfully increase the computational and engineering complexity of your pipeline. And three, not all libraries support these methods. I responded to that last one just a minute ago. Spark, MLlib, specifically, does not include random search. They only include grid search. So if you want to go down that path, which I recommend you do, you either need to implement your own, hope that someone contributes one up to the Spark mainline, or B, use a third-party tool that would be able to kind of help you explore this space without getting directly tied into the MLlib library itself. Computational complexity is definitely the most apparent problem that we have inside of hyperparameter search. All of these methods are complex, they involve large search spaces, and search is always computationally hard. Adding these methods should be done with full knowledge of that particular fact, and that no matter what you do, even the most efficient methods that you have, it's going to make your training pipeline more expensive, simply because you're going to have to run multiple trials just to actually see which method gives you better results. There are alternate strategies, like I've referenced, that are not covered here, most obviously Bayesian optimization, that can have even better speed improvements. But no matter what you do, you're still increasing the overall time that it takes to evaluate your search space. Really, grid search over a sufficiently large space guarantees the solution because it's an exhaustive search. Other solutions simply take the time, make the trade-off of making that search more tractable in practice while giving you guarantees, probabilistic guarantees, that you're going to be able to get somewhere near the optimal point. But of course, you always run into the possibility that, let's say in our previous example, 5% of the points inside of our space is not actually 5%. The optimum point does not cover 5% of our space. Instead, it could be extremely thin and extremely narrow. Overfitting, again, is a general concern in machine learning and is no less a problem here. And arguably, these repeated trials over the same data could accelerate the issue. Overfitting is definitely the most dangerous aspect of this kind of optimization work, and it can be self-reinforcing. In general, fortunately, standard strategies will apply. K-fold cross-validation tends to be the standard tool that is used, although there are definitely edge cases where it's something you're going to want to consider. This is, again, where human beings come into the factor. That kind of discriminatory action is where we've got a substantial improvement over currently implemented machine learning tools and libraries. The last slide that I've got for you here before we kind of close out this presentation is a reference to some other services that do this optimization. More and more over the last couple of years, we've been seeing more standalone services, as well as machine learning frameworks and libraries starting to put in capabilities for automated hyperparameter and model selection search. Caveating that nothing that I'm about to say is advocating for any of these tools or any one of the organizations. There are a couple of companies out there that provide parameter selection as a service. SigOpt is the one that I tend to see the most. They favor a Bayesian approach. They've got a really fantastic blog if anyone's interested in reading it. They've produced some of the best reading material, certainly. And I know a couple of organizations that have used them to effect. Deciding to use something like that is a case-by-case decision. There are other tools as well in the open source space. H2O, who I believe has a booth outside, is either releasing very shortly or has already released methodology for automated model tuning. sklearn has it in now. HyperOpt is a tool that has been publicly released that apes a lot of the capabilities of SigOpt in general. And then SigOpt itself is based off of a tool that came out of the Yelp labs in 2015, if my memory serves. They all employ slightly different techniques for hyperparameter optimization, but they don't always necessarily employ the same ones. So some have functionality that the others do not. I really like the quote from the Blizzard speaker immediately before me, who said that there shouldn't be any love for a tool. And I really support that, particularly in this particular space. The basic techniques inside of hyperparameter optimization are relatively simple to implement. They take a little bit of time to kind of work into the tooling that you have, but it doesn't take a huge amount of effort. A team of developers could do it relatively quickly. And it's something that we're going to have to, as a field, get very accustomed to, simply because research in this area is moving so quickly. All of that being said, you don't always need one of these services. Most of the frameworks that we're likely to work with, including MLlib, are going to implement at least some basic functionality, and the overall open source community does a great job of kind of building out technology that the frameworks don't already implement. I'm more or less at the end of my time here, so I'm sorry that I didn't leave enough time at the end for questions, but I'll be around immediately thereafter for it. But I do want to thank you for all coming in and listening to this, and hopefully there was something in here that was useful for those of you who have not already been exposed to this space. Thank you.